So in the last video, we saw then that the most desirable effect of a sodium iodide crystal is when the photoelectrons happen when the gamma ray comes in and creates a photoelectron. And then what will happen is you get all these blue photons coming out, or these UV photons start traveling through the sodium iodide crystal wherever that photoelectron eventually deactivated or went back into the valence band. So it's very important. These are UV photons, okay? And so the next part that makes the detector work is, this is sort of the extent of what the crystal does for us. So you can think of the crystal just purely as being an interaction mechanism for the gamma ray and causing these UV photons to exist. But then if you look very carefully at the detector, they also have a little thing tacked on at the end of it here, which was just sort of, for lack of a better word, called the base. And there's some electronics in here. So what happens then is when the UV photons come in, remember UV photons have a nice amount of energy to them, is you put a photocathode in the way. So now you are going back to your experiment that you did a while back. You put a photocathode here like this, and I wanted to draw that in a slightly different color here. So here's the photocathode. And what we mean by photocathode, again, is a metal whose work function is low enough that a UV photon can cause an electron to come off. So here we go. That's exactly what will happen in here, is if you sort of drill down and get really close here, the UV photon will travel in like this, strike the photocathode, and by golly, electrons will come off. And what you do with the photocathode then is you bias it with a high voltage on the outside. Let's see, I'll draw that in orange, I guess. Draw some bias like this. I don't know exactly how it would be connected, but something like this and like this goes out to some power supply, maybe to the tune of something like this. I'm going to draw the bias upside down to make my point here, 600 volts. And so this diode here, because it's on the negative of the battery right here, sort of has a negative charge on it. So what will happen is that the electrons will strike this and then immediately be sort of sucked on to another of these photocathodes, which is maybe down here and down here and down here and down here. And collectively, all these photocathodes are called dinodes. And so what will happen, let me track the trajectory of a white electron here. So let me get some white color going here. Okay, so what will happen is this electron will be ejected from the plate, and this 600 volts acts very much like the accelerating potential did in the photoelectric effect. We're not trying to cause the electron to stay on the plate, though. We want it to come off, and it does. And it'll sort of come off and fly down here and strike this dynode right here, which is a slightly lower potential. And so that'll cause a few more electrons to come off that'll go on and strike this dynode, which will cause a few more electrons to come off and it'll strike this dynode. And even more electrons will come off to strike this dynode, and even more will come off to strike this dynode. So this process that goes down like this, causing electrons as it goes here, is sometimes called an avalanche for obvious reasons. You know, 1, 2, or 3, or just a few electrons that were produced by those initial UV photons hitting the dynode here can produce upwards on something like maybe 1 million electrons by the time they get over here. So maybe by this point right here, we might very well have 1 million electrons. And you would be correct then if you're thinking, well, is this finally the detection current that we have? And yes, it would be. So on the very back end of this last dynode, or somewhere in here, is a wire that comes out of the detector, and this wire here is going to form your signal. So I hope you can appreciate the whole mechanism that happens here is essentially the gamma ray went in, and if you can get those photoelectrons to be created, UV photons are going to come out that travel through the transparent sodium iodide crystal, transparent to UV light. The UV light then sort of gets a photoelectric effect going on here, but the voltage doesn't hinder the flow of electrons, it definitely encourages them. Where a couple of electrons that come off of this first dynode slam into the next one, so 2 maybe make 10, and then 10 make 1,000, and then 1,000 make 100,000, 100,000 make 1,000,000, something like that. There's a big gain in this avalanche of electrons that comes down that is then piped out on a wire, and that will be your signal. So I hope you appreciate the whole process. A gamma ray goes in, and a signal, a current, comes out. And that's the basic gamma ray detection process. Now, you have to be a little bit appreciative of all the technology here, both growing the crystal and protecting it from the environment, and finding material that can efficiently detect gamma rays and also be transparent to this UV light and the thallium dopant in there. And I believe a Nobel Prize was won for this whole detection process here. And then, of course, you have the base of the detector. You can always see a metal cap on all these detectors that the cables and so on to connect to. Detectors are often run at something like 600 to 1,000 volts. You'll see that to bias these diodes so the electron avalanche can happen. So that's like one wire that will always go in, and another wire that comes out will be that signal. Okay, so I'll conclude the video then with sort of what you'll find then lab-wise sort of on the equipment level. So we don't have to go so microscopic all the time now that we can appreciate that essentially the detector sits here. Here's the detector, the sodium iodide crystal, and the gamma ray goes in. And basically a current comes out. Now, the one thing about the current is it's very, very small. Even the million electrons or whatever they get is just incredibly small. It wouldn't even make an LED light up or anything like that. So the very, very first thing you have to do when the current comes out of the detector like this is you have to amplify it. And so the amplifier, the schematic in electronics, is typically a triangle like that. And this is always called for gamma ray detection a preamplifier. And the preamplifier, or it just sort of goes as preamp for short, is a very specially designed amplifier that has an incredibly high resistance right here. So at this junction that it goes in here, the resistance of the amplifier is very large, as it has to be, right? The current coming in here is very, very pathetic. It's hardly anything at all. So you'd have to have some driving electrons that just doesn't require a lot of current to run. So you're presented with a very large resistance. And then once that's done, then you're pretty much in good shape. The preamp, then the current just comes out here, and you still sort of have at this point, I'll just go ahead and call it a voltage at this point, which is relatively strong. This you can start piping around and doing something with. And what you immediately do with it after the preamp stage is, of course, you put it into another amplifier. But this one is just called the amplifier, or the amp for short. So the question I usually get then is, well, would it be possible then, as long as you just have two amplifier stages, couldn't you just run the output of the detector right into the amplifier? And the answer to that is no, you can't. This pathetic little current, wispy current, isn't very strong, would never be able to run an amplifier directly. You always have to go into the preamplifier first. And this isn't really unheard of. I think preamplifiers exist for guitars and some musical instruments and things like that, where you have a very, very small current come in and you sort of boost it up a little bit first before you go into the main amplifier. So it isn't incredibly unheard of. Okay, so in the next video then, I'll discuss what sort of we expect to come out of the amplifier.